In this video, we will discuss the Navier-Stokes equation for the axial viscous flow along a circular pipe. Show that DDR of R DDR of phi is equal to 1 by eta into R ddx of P. Here, V is the velocity of pipe with R radius and eta is the viscosity. And ddx of P is the pressure gradient along the pipe. And at question number 2, that if the viscous flow takes place in the annular space between two concentric pipes of radius R1 and R2, where R2 is greater than R1, the maximum velocity occurs at radius R is equal to R1 root over R2 by R1 whole square minus 1 divided by 2 log e power R2 divided by R1. So this is a cylindric pipe. X, Y, and Z axis. So the solution since the flow is laminar, the flow is in the R direction. So since the flow is in R direction, so U component of the NS, so U component of Navier-Stokes equations in cylindric coordinate R theta z is U by dt plus U del U by del R plus V by R del U by del theta plus W del Z minus V square divided by R is equal to FR minus 1 by Z plus mu del square U divided by del R square plus 1 by R del U by del R plus 1 by R square del square U divided by del Y square plus del square z divided by del z square minus 2 by r square minus 2 by r square into del v by del theta. So we know that in steady laminar flow, steady flow, del u by del t is equal to 0. Then u is equal to ur, u of r, and del p divided by del r is equal to del p by del x, and p by r square tends to 0 when r is greater than 1. Okay, take a screenshot here. And now, uh, from that equation, we can write that 0 is equal to 1 by rho into del p by del x plus nu del square u divided by del r square plus 1 by r del u divided by del r, where the nu is equal to mu divided by g, sorry, mu divided by rho. Then um, del v by del x transpose this part into at this part. Del v by del x is equal to mu del square u divided by del r square plus 1 by r into del u by del r. Then we can write that r squared u divided by dr square plus du divided by dr is equal to r by mu into dp by dx of the ddx of p. Then from this equation we can write ddr of r du by dr is equal to r mu ddx of p. Then ddr of r dv by dr is equal to r by eta into ddx of p, where mu is equal to eta, the viscosity, and u is equal to v, the velocity. So this is the Navier-Stokes equations. Now we will solve the radius part, the maximum radius part. So from the Innes equations, we get that ddr of r ddr of v divided by eta ddx of p. This is the NS equations. So integrating both sides, both sides, we will get that our ddr of p is equal to r squared divided by 2 eta ddx of p plus a, where a is a constant. Okay. So for maximum velocity, we know that ddr of v is equal to 0, where r is equal to the maximum r. Then we will get that a is equal to, from these equations, a is equal to, if we put 0 here, we'll get a is equal to minus 1 by eta. Sorry, in this equation, from this equation, we'll get a is equal to 1 by eta ddx of p into r squared divided by 2. So question number 1. So from 1, we will get our ddr of p r squared divided by 2 mu ddx of p plus a. So ddr of p is equal to r divided by 2 mu, dividing these two part with r, and we will get dp by dx plus a divided by r, dividing by r, this equation. We will get this second equation. Now integrating the second equation, we will get v is equal to integration of r divided by 2 eta ddx of p dr plus integration a by r so r squared divided by 4 eta ddx of p plus l on r plus p. So the equation number 3. So when v is equal to 0, r is equal to r1, and small r is equal to 2. So from 3, we will get uh, 0 is equal to r1 squared divided by small r1 squared divided by 4 eta ddx of p plus a ln r1 plus b. It's number 4. And it's equal to r2 squared divided by 4 eta by x plus a ln r2 plus b is equal to 5. Take a screenshot here. Now from 4 and 5 equation, we will get a is equal to 1 by 4 eta into r1 square minus r2 square divided by ln r2 by r1 dx of p. We note it with number 6. But what is a? A is equal to minus 1 by eta ddx of p r square divided by 2. So we have minus 1 by 2 eta ddx of p r square is equal to 4 eta into r1 square minus r2 square ln r2 divided by r1 dx of p. Okay. So r square is equal to r2 square minus r1 square divided by 2 ln r2 divided by r1, or r is equal to r1 put over r2 divided by r1 whole square minus 1 divided by 2 ln r2 divided by r1. Okay, this is the proof. So now I will discuss different things, like for a steady, fully developed laminar flow of a viscous fluid through a circular pipe as in possible flow, the maximum velocity occurs at the center of the pipe. So we prove proof that the maximum velocity occurs at the center of the pipe r is when r is equal to 0. Okay, so we know that Vr is equal to 1 divided by 4 nu ddx of p capital R square minus small r square. So from the maximum velocity condition, we can write that dv by dr, or the dr of v, is equal to 0. So differentiate the both side, we will get uh, dp by dr is equal to 1 by 4 mu ddx of p into minus 2r. Okay, so minus 2r. So if compare the if I compare this equation with this equation, we will get that minus 2r is equal to 0 and r is equal to 0. So we can say that the maximum velocity occurs at the center of the pipe. Maximum velocity occurs at the center of. Okay, thank you.